Wouldn't it be nice if subnetting were just, easy? I mean, if you're like me, maybe math isn't your strongest suit that there is, and when it comes to IPv4 subnetting, you still do it on your fingers. Maybe because you watched Keith Barker's content a long time ago on IPv4 subnetting and he taught you the finger game. But if you're not, if you can actually rattle off subnets off the top of your head, you're blessed and feel lucky. So we go through the process of learning how to do IPv4 subnetting. Then what? We know how to subnet. Now it's time to actually design subnets. And that's what this skill is going to be all about. It's going to be all about taking that IPv4 knowledge that we have and actually applying it in logical ways to how an enterprise might design their address schemes. Now, there are some very key tenets to design in general when it comes to all aspects of networking. It has to be secure, it has to be stable, and it has to be scalable. So throughout this skill, we're going to refresh those three tenets and talk about how we could design all of these items with security, scalability, and stability in mind. Get ready as we talk about how to design an IPv4 address scheme. Let's get going. So we talked a little bit about what makes IPv6 special, about how it has some different functionalities and capabilities built into it that IPv4 does not have. What we should do now is start talking about how IPv6 addresses come to be in the first place. We're not necessarily talking about what are the commands that we use to configure them at this point. That's what the next nugget's going to be all about. What we're talking about now is stateless or stateful address assignment. Let's start talking about what that really means. So now it's time to talk about how IPv6 addresses really come to be. How did I get my computer to get that IPv6 address right here, this 2600, 1700, A40, 5020F? How did this IPv6 address show up on this computer? Because I didn't create this pool of addresses on my own. Just like how IPv4 addresses are allocated to ISPs and large research entities like universities, so are IPv6 addresses, and they're allocated by your internet registries. Now, this is different for pretty much every continent. In the United States, we have ARIN. The cool thing about IPv6, though, is we have so many IPv6 addresses that enterprises can register with ARIN to receive a block of IPv6 addresses. And why does this matter? Well, here's your enterprise right here, right? Let's pretend for a moment that you didn't register with ARIN. You go to your ISP and you tell your ISP, hey, I need to connect to the internet. I would like a block of IPv6 addresses. And the ISP hands you a /64 out of their gigantic amount of IPv6 addresses that they have. You then use something called prefix delegation. And not kidding, on a lot of enterprise devices, including like the Ubiquiti Unify line of devices or Cisco devices, prefix delegation is as simple as a checkbox or turning it on. Your edge router here will receive the /64, and then when your devices, like your enterprise devices or your IoT devices, perform a router discovery, that prefix that was delegated from the ISP to you is now what is going to be used for all of your devices in your enterprise, and that's how they get their global unicast address, the 2000 series. But what happens then when you leave the ISP and you go to a new ISP? Guess what? All of that public addressing that you had delegated from the first ISP goes away, and you're now going through the process over again. Probably not a huge deal, but if you do have publicly accessible resources like a website that you were using with IPv6, guess what? Now we're having to fix our IPv6 DNS services and maybe readdress our servers and things like that. And that could end up being a huge pain in the butt. So that's why we say if you're going to be designing an IPv6 network and you're going to be having publicly accessible services, you may want to register with ARIN, so that way ARIN gives you a set of global unicast addresses that you can use and advertise to your ISPs. That way they know how to get to you, rather than relying on them to delegate it. Now, it is also worth pointing out that maybe there is a scenario where you have two ISPs and they both delegate /64s to you. Guess what? This works perfectly fine. You can have multi-home devices. Every device in your entire enterprise can have multiple global unicast addresses. Keep that in mind. So both ISPs would make a reachable solution for you to your endpoint and your services. That's why we call this multi-homing, and that's again what makes IPv6 so flexible. We just have so many addresses. So that sets up an important design consideration about where you're going to get your /64s or the network address portions of your addresses in the first place. What about the host addresses? We know, based on the last nugget, that one of the processes that happens here is a device comes to life and it can assign itself a link local address. This is going to be an FE80/10, and then it can go using the neighbor discovery protocol, as opposed to ARP, to find out who its neighbors are, what their link local addresses are, and then from there, discover the routers and the global unicast subnets that it should be using. This all, up till this point, has talked about the first portion of the network address, the 2000, the FE80. What about the host address? This is a major talking point, is how do our hosts determine their IP addresses? The first thing that we can point out is that this can be statically or manually assigned on both the link local or the global unicast level. This does, of course, create more overhead for you. We can also use auto configuration. This is one of the coolest things about IPv6 in general, is that almost every device that supports IPv6 has the ability to assign itself its own host address, and it leverages the MAC address for this. In the next nugget, you're going to see this in action. I'm going to jump on the terminal and show you just how incredibly easy it is to get IPv6 up and running in your environment using auto configuration. But auto configuration comes in two very distinct and important flavors. And in order to set that up, what I'm going to do here is I'm going to clear the screen and we're going to talk about stateless auto configuration, or specifically it's stateless address auto configuration, SLAC for short. We're going to talk about stateful. This is going to be using something like DHCP v6, or a hybrid of the both. That can go by two names. Sometimes it's called stateless DHCP v6, or I've also seen it called DHCP v6 Lite. Let's first talk about SLAC. By using SLAC, we're using an auto config configuration. What a clever name, right? And it performs the operations based on how we've already identified. When it uses SLAC, it'll create a link local address and then insert the MAC address, and it immediately begins the neighbor discovery and neighbor solicitation phase. We're going through the neighbor discovery protocol here. Once that is done and it finds its neighbor, it can then move on to finding the router discovery using a router solicitation or a router acknowledgement. And this is how it can go about finding its global unicast address. Now, the global unicast address could do something like the 2600 as we've seen, blah, 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 for the network address. And then when it gets to the host portion, it can randomly assign something and check for duplicates, or it can use what's called EUI64. The EUI64 config is such a handy one because what it can do is it can take the MAC address, which is typically 48 bits, it splits the MAC address down the middle. So 24 bits are written here, and 24 bits of the MAC address are written here, and sandwiched in between them is an FFFE. There's one other thing it does, is the 7th bit that's listed here gets flipped. So if it was a 0, it becomes a 1. If it was a 1, it becomes a 0. The point is that it mostly resembles the MAC address with an FFFE in the middle. So using SLAC, our devices, at the moment the address is initialized, can create an FE80 link local address that's going to resemble the MAC address here. It can go through the neighbor discovery protocol process, find the router on its segment, and then using EUI64, it'll know what the global unicast address is from the router, and it can create its own host address based on the MAC address. It's really, really easy to configure because it's really, really dynamic. It's like it's only 2 commands on a Cisco device to make that come to life, and it's very handy. But there are some limitations when it comes to that. The limitations of SLAC might not be obvious at first, but then when you hear this, when you see it, you're going to go, oh yeah, well that kind of makes sense. DHCP is usually the protocol for dynamically discovering and assigning IP addresses on IPv4 networks. But what does DHCP also bring to the table? Options. Think about that. The default gateway is an option. DNS is an option. Your SIP server is an option. There are hundreds of options that come with DHCP that don't come with auto configuration. Auto configuration is really only concerned with what's my subnet, what's my host address, and how do I get off the subnet. It doesn't really care about things like DNS or your SIP server, and that is where Slack can fall short. And DHCP v6 is what solves that problem. It works the exact same way that DHCP does. We have a DHCP server, and we tell our clients they should perform discover requests to the server. They receive their addresses with all of the options back with it. But then we kind of take a step back. It is less dynamic there. We have less control. We don't use the neighbor discovery protocol and look for duplicate address detection using this. This is why they created a hybrid of the two. When we have stateless DHCP v6 or DHCP v6 Lite, what we're using Slack for the first portion of it. That way we actually get connectivity to the network using IPv6. It will initialize the Slack link local address as well as the global unicast address, and then leverage the options portion of DHCP v6. So using this, we can still get our DNS or our SIP server after we've performed auto configuration. So this is how we could start designing an IPv6 network to work within our enterprise. We now have to consider, how will devices discover or learn what their address is? Do we want to use a DHCP v6 server? Do we just want to use auto configuration? Or do we want to use a combination of both? That's really the big consideration when it comes to IPv6 addressing. Now in the next nugget, we're going to pull up a topology and actually work on creating IPv6 addressing, and then talk about scalability when it comes to summarization. I hope this has been informative for you, and I'd like to thank you for viewing. All of this talk about the capabilities and features of IPv6 and how to interpret an address and all of that stuff, when it actually comes time to jump on the command line and configure an IPv6 address, it's kind of anticlimactic, especially if you're using auto configuration. What we're going to do in this nugget is show you how you can quickly get IPv6 addressing both link local as well as global unicast on your devices, and test it out and just see if it's working. Keep in mind that the big deal about IPv6 design isn't necessarily about the subnets and which prefixes are we going to use. It's going to be more about the interior gateway protocol and how we leverage IPv6 when we're deploying things like OSPF v3 or ISIS or EIGRP v6. This is what we're talking about when we talk about deploying and designing an IPv6 environment, and that's why when you design your subnets, you need to keep the summarization points throughout your topology in mind. Anyways, let's get going assigning IPv6 addresses on our devices. So here we go. This is going to be the topology that I'm going to be working with throughout this course. And what we're talking about in this nugget is IPv6 addressing, how we can actually configure it, and how we should actually think about it in design. In an enterprise design, we're going to have a core tier. Right here in this little dash box, we're going to have a distribution tier. And then, of course, down here at the access layer, we're going to have an access tier. We may have layer 3 connectivity at every single layer, or maybe layer 2 up to the distribution layer. Learning those types of things are things that Jeff Kish is going to cover as we move along through the content. But one of the big things that always comes up when it talks about IPv6 or IPv4, really in interior gateway protocols, is summarization. Whether you're using IPv4 or IPv6, there is a real possibility that your enterprise network could grow from 20, 50, 100 subnets to thousands of subnets one day, and we don't want to overwhelm our core or our distribution layers with way too many routes. So when we design our IPv6 subnets, we may be looking at area 1 here or level 1 here. We may be thinking to ourselves, we want to group our IPv6 subnets as close together as possible. So that way when this switch here or this switch here goes to advertise those subnets out using something like OSPF or EIGRP or ISIS or even BGP, we can summarize that IPv6 subnet as it goes out towards the core or the other distribution layers. So if I had something like 250 subnets down here, I wouldn't want to have something like 2002:DB8:AA00:1111, and then in the same area have something like 2002:AB8:BB00:2222. You see, this would not be summarizable because probably the cleanest point of summarization would happen within like this first section. We need all of our subnets to be summarizable or as close together within this last block of the subnet mask. That way, when it gets to this point, they can be summarized upwards towards the core. So when it comes to IPv6 scalability, you need to think about how we're going to design our IPv6 subnets and where the summarization points should occur. It's almost always at the distribution layer where summarization occurs. But I did say we were going to see it in action too, right? Let's say we've got our own IPv6 block of addresses that we registered from Aaron, and now it's time for us to start deploying those throughout our network. If we want to use something like Slack, which will make these core routers come to life very easily, we can use it on, say, this link right here. This is going to be E00 and E13 down here on these addresses. So let's bring up the console of switch 16 here. I'll go into privilege mode, configuration mode, and we said this was going to be interface Ethernet E00. If I want to give this stateless auto config on the link local address, I'll simply say IPv6 address, check out my options here. Look, auto config is one of them. You can also see where DHCP-v6 could be configured if we had a DHCP-v6 server. Auto config literally lives up to the name, but it's worth pointing out even the other options here. We can assign a link local address or the global unicast address. Now, what do you notice the difference between those two is? The global unicast address has a subnet specified in CIDR notation, whereas the link local address does not. However, if we just use auto config, that's really all there was to it. I can give it a do show IPv6 interface brief, and look at that right there. There it is. There's my link local address that was automatically configured on Ethernet 00. The command, again, was just IPv6 address autoconfig. At the same time, I can go ahead and assign my global unicast address. We can say IPv6 address, let's say 2600 colon DB8 colon, let's give it the good old-fashioned dead beef. I can say // I'm not specifying an actual host address because when I use a /64 here, I can now specify EUI64. And recall, that means it's going to use the MAC address, split it in half, change one bit, and put an FFFE in the middle of it. I'll press enter, give it a do show IPv6 interface brief one more time. And what do you see here? We see something pretty familiar. The link local address is using that MAC address. The global unicast address is using an almost identical MAC address, with the exception that it split it with a FFFE in the middle of it. I don't know about you, but this is pretty cool because all we have to do is just say address autoconfig and IPv6 address EUI64, and it just handles the rest for us by using that MAC address. It's like it's magic. It's pretty cool. So now let's bring up the other side of that link, which was going to be switch 1 here on Ethernet 1.3. Very quickly, I'll go into configuration mode, Ethernet 1.3. I'll say IPv6 address, autoconfig to bring up the link local address. And then I'll also give it the 2600 DB8 deadbeef / 64 EUI64 and press enter. I'll just press end, give it a show IPv6, not 5, 6 interface brief. And check it out. Look at that. My addresses have now been assigned based on that MAC address. Again, noticing that the EUI64 did squeeze that FFFE in the middle of it. So the moment of truth, if I give this a ping IPv6 on switch 1, and I grab the global unicast address here from the other device on the endpoint, look at that. We've got round-trip connectivity. What about the link local address? I'll do the same thing with ping IPv6, grab the link local address. It asks me what my output interface is going to be. I'm going to say E13. No, got to make me type out Ethernet 1.3. And we've got round-trip connectivity there. Further, let's check out show IPv6 route. This is where it starts to get pretty interesting. We see my global unicast route is the only one that's going to be in the routing table because the link local IPv6 address is the only one that's relevant. The cool thing about it is that the communications between these devices will still leverage that link local address because that's kind of the entire point, is it's how it transmits interface information from one hop to the next. Keep in mind that the next step would be to configure it on all of the other interfaces that you have, maybe using autoconfig one more time. I'll just go into Ethernet 00 here, say IPv6 address, autoconfig, IPv6 address. This time we'll specify, again, keeping the address spaces close together, 2600 DB8, dead, but now I'll put dead B. So it's only 1 bit different, thus making it easier to summarize, and I'll say EUI64. Now that this device has multiple IPv6 addresses, it's time to start leveraging the IGPs like OSPF or ISIS to share the routing information from one node to the next. That way they know how to get to other global unicast prefixes within our own environment. But that's a discussion for other skills within this course. For now, this has been how to understand how IPv6 addressing can really work, designing things like how it should configure its own IPv6 address or use DHCPv6, as well as keeping in mind the scalability and the summarization points within the topology itself. I hope this has been informative for you, and I'd like to thank you for viewing. So there you have it. IPv6 is a robust and mature network addressing solution for you, and it's not that bad to implement in your environment when you're using things like autoconfig, EUI64, or even prefix delegation if that's what's given to you by your ISP. So that's been designing an IPv6 network. I hope this has been informative for you, and I'd like to thank you for viewing. Before we jump into actual IPv4 design, let's get a quick refresher about the components of IPv4 design. That way we know when we jump into it how we can take this knowledge and apply it to a real enterprise campus. Let's get going. Do you remember the first time you learned IPv4 subnetting? Maybe you were going for your Network Plus or your CCNA. That was kind of an overwhelming experience, wasn't it? The IPv4 subnetting is not a particularly simple thing. You get into the binary and how it all works. Before we actually jump into how we should take that knowledge and apply it to a real production environment, we should take a step back and just refresh ourselves on some of the key components about the IPv4 subnetting, RFC19 addresses, and even NAT before we move on, because these are all core components to how we design an actual network. And if any of that stresses you out about subnetting, don't feel bad. That only makes you a red-blooded network engineer. Recently, I was on my own YouTube channel taking a BGP CCIE practice exam, and I'm sitting there doing this on the video, kind of subnetting on my own fingers. It's just how it works, and it's just part of it. So let's dive into a quick refresher on IPv4 networks before we jump into how we actually design them. First things first, we need to talk about the classful boundaries. And when you think of a Class A address, what's the subnet that comes to your head? Probably almost all of you are thinking about the 10 subnet, right? And this is a big talking point already out of the gate. The 10 subnet is a Class A address, but guess what? It is not the only Class A address, and that's kind of the misnomer. That's kind of the mistake that we make as network engineers, is we forget that these classes are actually large ranges of addresses that are set up based on the bits that are in play here. For instance, Class A is really anything 0000 through 120, I guess it's technically 26, but we should put 127 here because 127 is a reserved address. What is really going on here is when we actually write our subnet out in binary, the Class A addresses always begin with a 0. They call this the higher order bit. So if I had a subnet that was 99.0.0.1, we know that this is a Class A address, first of all, because it fits in the range of 0 to 127, but I could also tell it's a Class A address because if I wrote this out in binary, the very first bit right here is going to be 0. Now this is where the trend start to emerge is when we go to Class B. The Class B high order bit, guess what? This is going to be 1, then 0. The first 2 bits are always going to be 1, then 0. And the subsequent result here is that this is a range of 128 dot whatever, x.x.x, to 191 dot whatever. And again, when you think of Class B addresses, you're probably thinking of that 172.x.0.0/12 subnet, which is 172.16 through 31.255.255. We move on to Class C, and this is where you see the trend emerge even further. The higher order bits now are 110. Can you guess what Class D is going to be? It's going to be 1110. Then Class E is going to be 1111. You could kind of get the trend of how this works. 0, then 10, then 110, then 1110, then 1111. Class C is the one that we all grew up knowing about because this is going to be our 192 section. We've got 192.x.x.x through 223.x.x.x. And again, we think about the Class C private address of 192.168, don't we? Because this is the one that, comes out of the box when we buy a device from Best Buy. Now, the interesting things about Class A through C is these are typically unicast addresses. Of course, the final bit or the final host address is going to be a broadcast address. As soon as we jump down into Class D, now we're talking about multicast addresses. Class D was specifically reserved for the multicast situation. When we had one server that needed to reach many different clients, we didn't want to initiate a unique session for every single one of them with unicast addressing. This could overwhelm the network as well as maybe the CPU of this particular server. So we created the one-to-many addressing scheme, which was Class D. And that's the entire point of multicast networking. Now, of course, we have a lot of multicast content coming up, so we're not going to dive into how multicast works too much because we've got dedicated skills coming up to that as part of the design playlist here. But it is important that we actually set up and recognize what a multicast address actually looks like. Multicast subnetting ranges from 224.x.x.x to 239 maxed out 255.255.255. I'm just going to write XXX here. And lastly, Class E is actually reserved for experimental networking, which is going to be 240 through 255, but not, of course, the broadcast address. We're going to cut this off at 255.255.254 because the 255, all 255s, is the maxed out all devices broadcast address. So these are some important talking points right now, is considering these are called classful boundaries. When we see a /8, that is going to be the Class A boundary. We're only talking about /8 networks. When we see the /12 in Class B, we're talking about the Class B classful boundary. When we see the /16 here in Class C, we're talking about the Class C classful boundary. And then, of course, we go into multicast and experimental after that. These are important because 9 times out of 10, actually, let me clear up the screen for a moment here so we can talk about this. When you see 10, how often do you see 10.0.0/8 out there in the real world? You don't. We always take this classful boundary of a /8 and we break it down into smaller usable pieces, because what we're really looking at here is millions of addresses. When we use all of the different combinations of addressing right here, we could do 10.1, then 1 through 255, then again 1 through 255. This goes on millions and millions and millions of times. In the Class B section, we get up to 65,535 addresses. When we get to Class C and we're actually looking at maybe these /24s, now we've whittled it down to 255 addresses. And then we also have to keep in mind that we need to reserve one address for our gateway and one address for our broadcast. So what you just heard me say was a pretty big talking point that we need to clarify and make sure you understand for the real world versus an exam environment. There is a difference between allocating addresses for users and endpoints and allocating addresses for hosts. Take a moment and think about a /24 CIDR notated subnet address, maybe like 192.168.1.0/24. Within that /24, there are a total of 256 addresses. That's the 0 through the 255. Now, when we take that /24, we know immediately that 2 of those are not usable. The 0, which is the network address, and the 255, which is the broadcast address. That leaves 254 usable host addresses. So in an exam environment, what you need to think about is, are they asking for hosts or are they asking for endpoints and users? Because that's different. Then in the real world, when we've got this 254 usable IP addresses, we immediately know that one of those, maybe the .1 or the .254, is going to be allocated for a router. So the remainder is what we can use for our endpoints or our users. So I wanted to clarify that before we went on any further. And if you hear me talking about this throughout the rest of this content, you need to pay attention to whether or not we're talking about hosts or if we're talking about end users. I always like to take one step further and go ahead and allocate that address for my default gateway and router now. That way I know how many endpoints I can actually have on my network. So the 255 that we're looking at here is really something more like 253. And this is absolutely critical for you to keep in mind. Look right here, me in the eyes. It is absolutely critical for you to keep in mind when you're designing your network that you have to factor in the broadcast address as well as possibly an address for the gateway. So when you see a /24, your head shouldn't go to 255 available addresses. It should go to 253 available addresses if you're factoring the gateway into that. You can only have 253 computers on this network if you want them to be able to communicate to a gateway. So we've talked about Class A networks, and we've even talked about how it's easy to confuse the Class A, B, and C networks with the RFC 1918 private addresses. That's 10, that's 172, 16 through 31, and then 192.168. whatever, that all make up our private addressing. And then this becomes another critical talking point. Again, we've heard this a few times, this always gets brought up, but we have exhausted all of the IPv4 addressing schemes available to us. That's why we had to create RFC 1918 and the private addresses. That way we could assign these addresses to any of our devices and any of our sites in a private manner. But these addresses right here are not available on the internet, and that's where we have to bring NAT or PAT into play. If I have 253 privately addressed devices in my enterprise and they need to reach out to the internet, but the internet doesn't accept 192.168s or 172.16s or 10s, how then do we get these 253 devices on the internet? And that's where we bring network address translation into play. As our devices talk to the router will translate their internal address into a publicly routable address, something like 44.32.99.1. And I just totally made that address up. If that's your address, I'm sorry, but there you go. This is just a randomly Class A addressed public address. The router maintains session knowledge, or where a network address translation has taken place from within this network, so that way when reply traffic comes back, it gets translated as it comes back into the network. So why are we talking about all of this? Why does this really matter? Here's the thing. We can't just throw subnets at our network and then hope that everything's going to work just fine. It takes careful planning and understanding about the components of each one of these octets and what they can actually represent within our network. And then we have to consider things about where traffic gets translated through our network, where it can get natted and where it can get padded. This even becomes an issue when we go through mergers and acquisitions and then two companies are using the same address space. All of this stuff matters when it comes to designing a network solution. So over the coming nuggets, what we're going to talk about is how to take this classful information and maybe break it down into smaller subnets, and then actually design each one of those octets to mean something. That's the entire point of network design. So that's been just a refresher on our IPv4 skills. I hope this has been informative for you, and I'd like to thank you for viewing. Now it comes time to think real world. We understand how IPv4 works and subnetting works, but what is a real world situation where we would actually have to use it and make a design scenario? In this nugget, what we're going to do is we're going to take one network and actually talk about the components that should actually build up those 4 octets that we need in order to create an IPv4 subnet. Let's get going. So now it's time to actually take those IPv4 skills and put it into action. Here's the thing. When we do this, we're going to be met with constraints. We're going to be met with rules and guidelines about how we should design our network, or at least we should think about what these rules should be. Maybe we're the decision maker on what the rules are. The point is we can't just throw a gigantic subnet at it and hope that it works fine. We need to think about the future. We need to think about scale. We need to think about stability, and we need to think about security. So let's start off with taking the 10 Class A subnet. This is 10.0.0/8. The first question I'm going to ask myself is how many devices need to be connected into this network. So I'm going to put number of devices/hosts. This may be the most important thing to factor in when it comes to designing a subnet. We need to think about how many devices need to connect to this network and whether or not they should be separated from other networks. For instance, let's consider for a moment that we have 200 users on our campus. And maybe some of those users have a desktop, others have a laptop. Almost all of them have a cell phone, and some of them may even have a tablet. Now here's the other kicker. That cell phone and that tablet are not corporate issued. Those are bring your own devices, and we don't control what goes on in those devices. What are they really accessing on their device? What are they really downloading? And this becomes now a security question mark right here. So my first question actually goes, do I want people's cell phones and tablets to access the same resources that I want their corporate desktop or our corporate servers to access? And the answer is no. So each user will either have a desktop or a laptop, and my first consideration is this network needs to hold 200 hosts, and we shouldn't factor in their cell phone or their tablets. We should create a separate network for that. You can make the exact same argument about IoT devices, which are things like cameras, thermostats, this day and age, doorbells, or card scanners. You could make the same argument about servers and printers. We want all of these to be on their own unique networks. So if I'm only focusing on the task at hand, which is designing a subnet for just the user's data, for their actual corporate data, I'm focused in on 200 users, and this becomes my first subnetting question. We're all pretty familiar with the /24 subnet, because that's what everyone uses this day and age. And that /24 subnet, we know, allows 253 hosts because one of those is eaten up by the broadcast and one of those is eaten up by the gateway. If I were to slide this up to a /25, what happens? The number of available hosts gets halved really down to 126 because, again, one of those is eaten up by the network address and one of those is eaten up by the broadcast address. So a couple good things come into play here when we're actually doing it like this and we choose a /24. First of all, we meet our minimum requirement of 200, but then we have an additional 53 for growing room. This is another very important point, is that we want to have growing room. That way we can expand our resources and expand our user group, because we want our company to keep growing, right? That's the entire point, is that the business should keep growing and we should keep hiring. So by doing the design like this, with a subnet like this, we actually have 53 additional users that we could add, and that makes it scalable. So we've kept security in mind here because we're not running all of our devices on one subnet. We're going to break it out, but we've also got scalability in mind here because we've got the ability to grow a little bit. This begs the question, Knox, why not just go with the /23 and get the 500 whatever devices here? See, I'm so bad at subnetting, I can't even think of it off the top of my head. That would be like 510 usable addresses, I think, because this is going to be a gigantic broadcast domain, and it eats up our ability to use those IP addresses somewhere else. We don't expect to add more than double our addressing space in the near term. This even begs the question about stability. Like when we have a broadcast domain that is that big, when the broadcast domain exists of 500 devices, there could be a lot of broadcasts going on, and this could actually be a problem. And we may want to limit it, especially if we're using legacy hardware that's kind of older and its processing power and ASICs just quite aren't up to snuff the way we want them to be. Limiting the broadcast domain may actually be a good thing for us. That way we control how our switches switch and how our routers route. So with this design of a basic subnet, we now have things like stability, scalability, and security in mind. We're separating all of our different devices. That's the first and most important one. We're separating our corporate data from the devices that could be compromised, like cell phones and tablets and IoT devices. We also have met the requirement of how many users need an IP address. And lastly, we've talked about stability, about not growing it too big and having a gigantic broadcast domain. Now let's talk about one of the important things that we should consider when it comes to actually designing our subnet. First of all is the gateway IP. It is a best practice to use either the first usable address or the last usable address as the gateway IP. So to pick on the 10.1.1.0/24 subnet, we would want the gateway IP to be 10.1.1.1 or 10.1.1.254. I don't know why, but I'm so attracted to that 10.1.1.254. I always thought, like, hey, that's really cool. It's kind of edgy to use the last address. And some devices out of the box, they really do use the last IP address as their default IP address. It's really up to you and whatever you want to do as a best practice. But whatever you choose, don't use the last bit on one subnet and then a completely different design on the other one. If you're going with .254, use .254 everywhere. That way it's standardized and understandable. If you go with .1 as your gateway address, all of your gateways should be .1. Don't mix it up because that could be really confusing, really hard to document, and really hard to troubleshoot and maintain in the future. Beyond that, we need to pay attention to these octets themselves because these octets should represent something. Now, the first octet is 10. Not much you can do about that because that's what RFC 1918 dictates as the actual octet that we need to use for a private address. And people tend to go with 10 so that they can use the other octets to actually represent something. In a lot of cases, the second octet actually represents the site or the area or some sort of geographical locations like a continent. And this will make a lot more sense when we get to the next nugget and we start talking about the enterprise campus design. But maybe we have 3 buildings here. We want this building to be 10.1. We want this building to be 10.2. And we want this building to be 10.3. So in this case, if I were to set this to 1, when somebody reads my IP address and they see the scheme, they would know that this 1 is representing where in the world this actual IP address or this subnet is going to be located. Then the third octet here almost always is going to represent the VLAN. You see, within these buildings, we may have multiple addresses or subnets for data, IoT, server, and so on. And all of these will exist on different VLANs, like VLAN 10, VLAN 20, VLAN 30. So when I set this address to VLAN 30, I see now that, okay, this is my private address, it's in building 1, and this is VLAN 30, which if I look right here, that means this is my server subnet. And then since we chose to go with a /24, we know that the addresses that are available to me are going to be the 253 addresses. So maybe my gateway is 1, so my usable addresses are going to be 2 through 254. So the basic subnet design is now in place. We've considered the scalability, security, and stability options that are important when it comes to actually designing a subnet. Then we talked about what each one of those octets could or should actually represent, as well as how to even set up the gateway addressing in the first place. That's been designing a basic subnet. I hope this has been informative for you, and I'd like to thank you for viewing. So now we understand how there could be constraints when it comes to actually creating an IPv4 subnet, things that we have to think about and factor in. But now we need to think even bigger picture. How is this going to work across our entire enterprise campus? That's what this nugget's all about. We're going to talk about subnetting throughout an entire business. Let's get going. So this is it. This is the real world scenario here. This is what an enterprise campus is probably going to be laid out like. Now, not every large campus is going to be like this, or not even small to medium campuses are going to be like this, but it could be some variation of it where we've got different buildings or different geographical areas that are all connected and communicating together. Now, you're going to learn a lot more about the enterprise hierarchical model, but the idea is that we have a transit area. This is called the core, that our other areas pass through when they want to communicate to each other. And it looks kind of like that. The distribution layer here is what's going to be handling the majority of our routing, and then the access layer is where all of our endpoints are going to be. Now, we've denoted these here with desktops, but you should think about those interchangeably as servers, as IoT devices. This is going to be the world's worst camera. Computers, laptops, cell phones, you get the idea. All of that is what takes place out here on the edges, and this is where the majority of our network design and subnetting is going to take place. In fact, the very next nugget is going to be a subnetting challenge where we have to meet unique requirements for this specific yellow area. What happens a lot of time in this situation is that we have this geographical area and we give it a block of IP addresses that we then whittle it down into different subnets given our constraints. Remember in that last nugget where we said we had 200 users and we had to think about things like the gateway and should the subnet share data with other types of devices? We kind of had to go through all of that to design one specific subnet. If we look at this diagram here, we see things like this area, this yellow area, has been given the block of 192.168.3/24. And what really happens is down here, we have different subnets, I'll denote them with different colors, that are going to be a piece of this /24. And the act of creating that is, of course, variable length subnet masking, or variable length subnetting, whatever you want to call it. So here in area 3, I see that my given address range is 192.168.3. In area 1, my given address range is 192.168.1.0/24. And my given address range here is in area 2 is 192.168.2.0/24. So thinking about what we went through in the last nugget, can you see a little bit of a trend that's taking place here? We have our private address space given right here. This is 192.168. That represents our private spacing. Then this octet here represents the area that we're working in. So area 1 has this right here. Area 2 has a 2 in this octet. Area 3 has a 3 in this octet. What will more than likely take place then is we will create VLANs on these access layer switches, and those VLANs will be represented in the 4th octet. So if I were to take switch 19 here, and we say that switch 19 only needs a subnet for 2 hosts, I may create the subnet 192.168.3.4/30, and I would use VLAN 4 in order to do that. One address would be eaten up by the gateway. This /30 allows for 2 hosts. The VLAN here, VLAN 4, is represented in the 4th octet. The next available subnet would begin with 192.168.3.8. Maybe in that scenario, I need 14 hosts. So I'll create VLAN 8 and set that to be a /28. And this is kind of the gist of how the variable length subnetting would work and how we would design our IP structure with the VLAN and the area in mind when we're using something like a Class C address. Of course, this is much easier when we use a Class A address because the area will get its own octet, and then the VLAN will get its own octet, and then the host will get its own octet. We could actually have more addressing that way. So that's why you see most enterprise campuses go with a 10. But this sets up the next major talking point, and that's what happens when we run an interior gateway protocol, something like ISIS, OSPF, or EIGRP. If we were to run this throughout the entire campus right here, every single one of those little bitty subnets like the /30s, the /29s, and the /28s would be advertised all the way down to these access switches and all the way down to those access switches. And all of their VLANs would be advertised all the way up to here. And the routing tables would be just gigantic with these tiny little bitty subnets. We now break into an issue where we lose our scalability because our devices are going to be overwhelmed by so many subnets. These types of routing protocols, ISIS, OSPF, and EIGRP, they are dynamic routing protocols. They find their neighbors and they perform mathematical computations and algorithms in order to find the best path from one point to the next. So when one of these little subnets goes down, maybe an interface flaps or something, every device within the entire network starts screaming about it, and they start trying to find, oh, what happened? We got to get back up. We got to reconverge. And this is what happens when one tiny little subnet goes down. You see what's happening on the screen right here? All of this communication. It becomes a big scalability problem because now our entire campus is trying to reconverge. So one of the ways that we should fix this is on the edges of our areas, what we do is we perform summarization. Instead of having all these /30s and /28s and /29s and /25s advertised throughout our network, when it gets to the boundary of the area, we just roll them up or sum them up into one gigantic /24. So that way down here in area 2, they have a route to 192.16, let me write that again, .168.3.0/24. And when this /30 goes down, this area right here will freak out about it, but these guys don't know about that route. They don't know about that specific route. They just know to get to any of the 192.168.13s, punt it up to these routers here, and they'll figure it out. So we solve our scale problem when we implement summarization at the boundaries. That's going to be very important. It's also important to understand what stubs do when you get into those individual protocols. OSPF has stubs and EIGRP has stubs. You're going to learn more about those in the upcoming skills, but those are also great places to actually control what happens when a route goes down and it stops this convergence and scalability issue. So the big thing that we're trying to do here is we're trying to bring the enterprise campus into view and see how a different subnet could be designed so that we see the private address, the region that it's in, then the VLAN that it could be serving or operating in. Also keeping in mind our summarization points right here on the borders. That way we don't have scale problems, or more importantly, IGP convergence problems when one of these little bitty routes down here goes down. So that's been understanding the enterprise infrastructure when it comes to IPv4 subnetting. In the next nugget, we're going to take this challenge up a notch and talk about how to actually do a design given constraints for one particular area. Let's get going with that. In the meantime, I hope this has been informative for you, and I'd like to thank you for viewing. Our final nugget on IPv4 address scheming is going to be the real-world challenge, creating a variable length subnet challenge. So what we're going to do in this nugget is we're going to set up a scenario. We're going to pause it as you try and work through it on your own, and then we'll come together at the very end and talk about what the solution on how to design this particular subnet is going to be. Let's get going. So our final challenge is to actually design a subnet or a group of subnets for an actual enterprise campus, and that's what we're going to do in this particular nugget. What we're focused on here is Area 3. Again, this is 192.168.3.0/24. So we have 253 addresses that we can work with here at this point. But what's happened now is we've decided we don't want this just to be one gigantic /24 broadcast domain. We need to actually segment these down. We need to have smaller segments of it. So here's what we're going to do. Our challenge is, first of all, we have a subnet that we need for hosts, and we need 60 hosts to be available within that particular VLAN. We have a servers VLAN that we're going to create that's going to need to have 8 server subnet addresses. We're going to have a voice subnet that we need to create here. That's going to need 43 phones that we're going to support. And lastly, we're going to create a IoT subnet here that needs to support 14 IoT devices like cameras or thermostats. So this is our challenge. We're going to actually go about creating these VLANs. Go ahead and just kind of draw it up, pause the screen, and tell me how you would take this 192.168.3.0/24 and break that down into these different subnets. Go ahead and pause the video and actually work through this, and we'll come back to it when you're done. So here's my plan of attack. Here's how I would handle this situation. The first thing I would do is I would actually reorder this list to have the biggest ones first and then the smallest ones second. So I would actually write this to be more like hosts need 60 addresses, voice needs 43 addresses, IoT needs 14, and servers need 8. That's how I would handle this. So let's start with 192.168.3.0 and create our first block of addresses. Now we know here that we need 60 addresses, and if we're trying to keep it nice and tight, I'm thinking to myself, a /24 allows for 253 addresses. A /25 is going to be 126, and a /26 is going to be 62 addresses. So my first subnet I would choose to be is 192.168.3.0/26. With that in place, I know my next subnet is going to start from the .64 address. So we're going to write 192.168.3.64. But now the question is, what subnet mask do I get it in order to actually support the voice subnet? Taking this down a little bit further, if I do a /27, this drops my available hosts down to 30, and that does not meet my requirements for voice. So yet again, I'm going to have to use a /26 in this place. So my screen's getting kind of messy. What I'm going to do for a second here is I'm just going to press the clear screen and rewrite this, and we'll come back to it so it's actually looking a little bit cleaner this time. Okay, that looks a lot better, and now I can follow along. Now I've got the host, the subnet that I want to make, and how many hosts were required, written in black here, and that's kind of the theme that we're working with. So now on IoT, because we've got the /26, because we had the /26 here on voice that was ending in 64, we now know that my next available address is going to start with 192.168.3.128. But what's the next slash? That's going to be the question, and it needs to support 14 addresses. So again, kind of just drawing it out in my head, /31 supports 2 IPs, /32 supports 4 minus 2, which is for the host. /30 supports 4, which is for the host. /29 is 8 minus 2 for the host. 28 is going to be 16. Oh, we got a winner. Look at that right there. -2 for the host because we've got 1 for the broadcast and 1 for the gateway. My subnet mask here is going to be a /28, and that leaves the last one here for servers, which I already got. But check this out. The /29 isn't going to cut it, because what we really have here is 8 minus 2, which is 6. So if I were to use a /29 right here for the servers, that wouldn't get the job done because we would still have 2 leftover servers. So I have to use a /28 yet again. In this case, the servers is going to be 192.168.3.144/28. Now remember what we said about VLANs too. You kind of want this section right here to correspond to the VLAN ID that you're going to be using. Now, it's not particularly ideal to use VLAN 0 for hosts, but that's kind of what you have to deal with when you're using a 192.168.whatever address, is that's the situation. And this goes back to, again, why we typically choose to go with the 10s, because we can use an entire octet to represent our VLAN, which is going to be that third octet. So that's been working through a variable length subnet masking challenge. I hope this has been informative for you, and I'd like to thank you for viewing. So there you have it, IPv4 addressing in the real world. We now understand the components about how we should design our actual IPv4 addressing scheme, keeping in mind things like geographic location or sites, as well as the VLAN that's going to be in play, and then the constraints about what our requirements really are. Things like how many hosts do we actually need for the subnet, and where should our summarization points be so that we're not flooding these subnets throughout the entire network. I hope this has been informative for you, and I'd like to thank you for viewing. Can we pause for a moment and be real? Let's just be honest with each other for a second right now. When we see IPv6 on a blueprint or on an exam itself, there is a collective groan where it's like, do I have to? We do. We have to. IPv6 is here. It is ushering in a new era. And if you ever break into a service provider network, or if you start working with mobile devices or things like that, you'll see IPv6 is dominant. So we need to understand IPv6 and how it's ushering in the new era. We need to understand the basics about how to read an IPv6 address and how we can also plan for them within our enterprise. So by the end of this skill, you'll understand more about the IPv addressing schemes that are available to us and how we can actually implement it within our enterprise. Let's get going. So I'm going to go out on a limb here and guess that at this point you've heard about this whole IPv4 exhaustion thing. We're out of IPv4 addresses, and that's why we created IPv6 to usher in this new era of IP addressing. And in order to understand how to use IPv6, we need to understand how to read the IP address in the first place. But here's the real kicker. Here's the big surprise. Here's the spoiler that you'll figure out by the end of this nugget. IPv6 is more than just an IP address. We actually made some improvements on top of IPv4 within IPv6. Things like built-in IPsec security, things like MTU path discovery, things like auto configuration. That's going to be a big talking point as we progress through this skill. So before we jump into how those things actually work, let's first take a look at the structure of an IPv6 address. So it never hurts to get refreshed on how to read an IPv6 address because there are some nuancy things to it. It's all about those zeros, isn't it? So let's talk about how we can read an IPv6 address. That way we can move our discussion forward and we see some odd looking addresses. We don't freak out. We know exactly what it is that we're looking at. And you know what would be really fun? Instead of just making up an IPv6 address on the fly, let's actually talk about real-world IPv6 addresses. Let's take a look at the ones that we have on my local computer right here. If I bring up Windows Terminal real quick, look, you can see I've got PowerShell for Windows open, as well as Windows Subsystem for Linux, because IPv6 is running on both. From the Windows side of things, I'll give it an IP config, and if I scroll on up, look at that. You see these big whoppers right here? This is a first major talking point that we should actually bring up about the functionality of IPv6, and that's that we have so many IPv6 addresses that your devices could actually end up with multiple IPv6 addresses. Sometimes they call this IPv6 multi-homing. And this actually sets up our big talking point within an IPv6 address. IPv6 addresses are 128 bits in length. That's much bigger than the 32 bits in length that we're used to when we see an IPv4 address. A very quick and snappy Google search yields this result, that this is how many addresses that really is. I can't even begin to tell you how many that is. I've heard that that is enough for one IP address for every grain of sand on the earth like 100 times over. Point is, there's a lot of IPv6 addresses out there, and that's why we can assign multiple IPv6 addresses to devices. That way they can have different paths or different locators within an address itself. So if we're starting to talk about an IPv6 address, we know that it could be a /128 or below. It could have 128 bits. Typically, though, when we see an IPv6 subnet, we see it as a /64. You can think of the /64 in IPv6 subnetting as kind of the equivalent to a /24 in the IPv4 world. It's just very common to deploy that and use that as your subnet design. This is plenty of address space for all of the hosts in your network, but it also allows for 64 bits to be used for host addressing, and that's going to be a big deal when we start talking about auto configuration and things like EUI64 or SLAC. Let's bring my terminal back up on the screen for just a moment, and I'm going to point out two fancy looking addresses right here because there's some interesting stuff that's going on with these two IPv6 addresses. Again, we're going back to that point that we made earlier, is that it's not uncommon for your devices to have two IPv6 addresses. And how did my computer get these IPv6 addresses? We're going to address that, what a pun, as we get later down through this skill. For now, we're just talking about how to read and interpret this IPv6 address. If I were to give it an ipconfig/all and we scrolled back up here, what I'm going to do is I'm going to copy this address and I'll just paste it in right here. And I'll copy the other IPv6 address that's written all the way out, and I'll paste it in right here too. Let me clean up the screen just a little bit, that way give us some room to work. And we're going to talk about how these IPv6 addresses really came to be. If you're looking at these and thinking these kind of look like MAC addresses, you may be right, because here's the thing. Lots of IPv6 addresses can be derived from MAC addresses. We're going to talk about that again later when we get into address configuration. The big thing to keep in mind right now with IPv6 addresses is these are specified in hexadecimal. We have a 128 bits that we can work with, and you see these colons here, again, very similar to a MAC address. Each of these are 16 bits. We have 1, 2, 3, 4, 5, 6, 7, 8 of these sections, these 16-bit sections that we can work with. And sure enough, 8 times 16 equals 128. Now, like I said before, a lot of IPv6 addresses, especially in enterprises or even your home, are going to be a /64. So if we have 8 of these little sections, I can go 1, 2, 3, 4, and whoop, draw the line right here. And guess what? Now I see that this is going to be my network, and this is going to be my host address. We've focused on the one here down here that has all of the items already spelled out for us. Now let's peek our eyes right up here. This again is a /64, and if I go 1, 2, 3, 4, look at this, we got these double colons here, and draw the line. My host address is simply just 437. So why the difference? Why is one spelled out and one not? This is actually a pretty important nuance and a way that we can make IPv6 more readable. Check this out. Let's pay close attention now to some of the details in these IPv6 addresses. For the most part, when I look at the IPv6 address that's at the bottom of the screen, all 16 bits are spelled out with the exception of this guy right here, the A40. What's going on with that? Why did that happen here? One of the first rules about IPv6 is that any leading 0 is dropped out of the address. So under the hood, we've got 2600, 1700, 0A40. That leading 0 gets eliminated right there. Then the rest of the address is completely spelled out just like this, and that is our global unicast address. We're going to talk about the types of addresses in a later nugget. Then we go up here. What's going on with this? We're actually missing quite a few of our little 16-bit chunks, aren't we? In fact, we're missing 3 of them. The ::" signifies that there were no bits set in between this F and this 4. So if we were actually writing this out, it would be something along the lines of 2600, 1700, 0A40, 502F, then a whole bunch of zeros. 1, 2, 3, :, 1, 2, 3, 4, and then, of course, there's another leading 0 dropped here, 0437. That's what this whole address is when it's written out, and this is why we're cleaning things up. This is one of the cool things about IPv6, is the superfluous zeros are removed from the address. So a leading 0 here and a leading 0 here got dropped, and then the series of zeros in these 16-bit sections were all removed by the double colon. Of course, this does set up the one one rule about the double colon is you can only use the double colon one time. You can't have a double colon here and then use it again down here. Now, if I bring back my terminal one more time, astute observers may have noticed some interesting things about these IPv6 addresses. Let me, clear the screen and bring this back real quick. What do you see here on the screen? We see some IPv6 addresses that start with 2600. We see some IPv6 addresses that start with FE80, and then some colons. We know what that means now. And then if I scroll down further, we see some that are FEC0. There are different classes of addresses, just like there are different classes of IPv4 addresses, and these leading 16 bits tell us a whole lot about the address and what is it really used for. That's what the next nugget's going to be all about, now that we know how to read an IPv6 address. I hope this has been informative for you, and I'd like to thank you for viewing. Now that we understand how to read an IPv6 address from one end to the other, and we understand a little bit about the subnetting process of an IPv6 address, what we should take a look at now is recognizing the different types of IPv6 addresses there are. We can do this with IPv4. Think about it, you could quickly recognize a private IP address or a multicast address or the different classes of addresses. IPv6 has similar things where we can look at an IPv6 and see, is this a link local address? Is this a multicast address? Is this a global unicast address? And we'll understand what does that really even mean by the end of this nugget. Let's get going. All right, so this is where it starts to get fun. This is where we start to talk about how IPv6 is really used in the real world. And let's start getting into it and start talking about this first address that we see on the screen, the 2000:/3. Now, obviously, we know that the colon mean there are a series of zeros. Interestingly, this is a /3. Only the first 3 bits are really used to identify the network here. The 2000::, is what we call the global unicast address. I mean, this kind of dates back all the way back to the early IPv4 days, where every device on the network got a public IP address. Remember? I mean, maybe you don't remember that, but universities in particular, this is really popular in United States universities, where you can go onto campus and, connect to Wi-Fi, and you look at your IP address and go, wait a minute, that's not a private IP address. That's a global address. That's actually something that, because universities were doing research in the early days of the internet, they actually reached out to their address registry. Like in the United States, we have ARIN, where you could reserve IPv4 or IPv6 addresses. Universities got blocks, huge blocks of IP addresses, and that's how they assigned all of their devices. The devices still to this day on many campuses get a public IPv4 address, and that's exactly what the global unicast address in IPv6 does. Because remember, we have so many addresses, we now have a way that we can uniquely identify a device to the public internet with the global IPv6 address. If I bring my terminal back on the screen again, we can now take a look at this right here or right here. I can now immediately identify these addresses as my global unicast address. This is how this PC right here is represented to the rest of the world. There is no network address translation when it comes to IPv6, or it's really frowned upon because we have so many addresses now that we can uniquely identify them in the world. So the big thing that you should keep in mind, first of all, is that when you typically see a 2 at the very beginning of an IPv6 address, this is a global unicast address, and it's used to uniquely identify a device to the entire world. Jumping back now to the diagram, we see that we have a couple here. This is FEC0 and FC00. The FEC0 is called a site local address, and this is kind of like a private address space that would be used by an entire site. Now, some publications may tell you that this address space, the FEC0, is deprecated and no longer in use, but the astute observer, again, on the previous nugget has already seen that it is very much still in use. I'm running VMware Workstation on this computer, and as a part of that, it creates these network adapters, and the DNS servers are using 3 site local IPv6 addresses. They all begin with FEC0, and that's how I can identify them. But in the event that it actually is becoming deprecated, we are now moving to the unique local unicast, and this is kind of what it sounds like. Instead of a global unique unicast address, we have a local unique unicast address, and this is basically the private address spacing of IPv6. Again, Not many people use private address spacing in IPv6 because there's no real need to unless you're trying to hide something. Really, in enterprises and even service providers, most addresses and addresses that are handed out today are global unicast addresses. So now it's time to talk about the FE80 address, and this is going to be one of the most critical addresses to actually understand because it's one you're going to see on nearly every single IPv6 enabled device that there is. The link local address is what we're talking about when we talk about FE80. And this is only significant on a link between two devices. Maybe these devices are routers like I'm drawing here, or maybe they're a router and an endpoint like a host. The big thing about link local addresses is that this is how the network is actually stood up and configured and comes to life, is by using these link local addresses. You see, IPv6 enabled devices don't use ARP. In fact, they don't even really use broadcasts. So if I write these down, I'm just going to put a big X over them right there. Instead, when the host computer like this one comes to life, it can assign itself a link local IPv6 address and then start the discovery process, kind of like DHCP, or exactly like DHCP, trying to determine if other devices are on the network speaking the IPv6 language. It will perform a neighbor solicitation, trying to find out who its IPv6 neighbor is. So the host machine here will send a neighbor solicitation out the link towards this router here, and the router, who is also running IPv6 and also has a link local address, will respond with a neighbor advertisement. And that's how they know who their next adjacency is. The same thing would happen right here between these two routers. And depending on how you've set up your IPv6 environment to work, it can take it a step further and start performing router solicitations and looking for router advertisements. So our host here may start looking for what its default gateway could be, or if it had multiple default gateways, it could find them this way by soliciting, are there any routers in this environment, and receiving a router advertisement. The router advertisement would respond with things like what the global unicast address is. And guess what? Guess how my device, the one that we've been looking at this entire time, guess how it came to be? Guess how it came to get this address, these 2,600 addresses that we've been looking at. Exactly this exact same thing. It created its link local IPv6 address that we're seeing highlighted right here on the screen. It went through the neighbor solicitation and neighbor discovery phase. It then learned about what the global prefixes that it could use from the router would be, and it learned that the next hop to get out of this network is going to be using that link local address. That's a really important aspect to really understand and grasp and conceptualize under the hood, is that when it comes to a next hop, typically within an IPv6 network, you're going to see the next hop is going to be the link local address, because even though it's only specific to that link, it can go to the next address. So it learns about the global prefix, about how it can identify itself to the world from the router using the 2600 subnet that we're seeing here on the screen. But when it's time to get out of the network, it only has one little link away to get to the router, which is that link local address. Now, we still have a lot more to talk about how this operation really comes to life, and we're going to talk about that in an upcoming nugget when it comes to how we can statelessly or statefully handle address assignment, and we're going to get to that. For now, you just need to know that the link local address is really what brings everything up and starts bringing things to life, and this is how it makes next hop decisions, is almost always based on the link local address. Now, the last one that we're going to talk about is FF00. This is multicast addressing within IPv6. So if we pay close attention here to the /A, that means the first two will always be FF, and the last two could change up a little bit. Here's the thing about multicast addressing in IPv6. We're kind of fortunate in this regard that it didn't change a whole lot from the IPv4 addressing schemes. Think about OSPF for a second. OSPF communicates in IPv4 on 224.0.0.5 or 0.0.6. And then we can also even take it a step further and think about EIGRP, which communicates on 224.0.0.10. When we talk about this in IPv6, the only thing that really changes is the first section. We can see FF02 is what's going to be the multicast address in IPv6, : and then for OSPF neighbor adjacencies, we'll see it use : 5. For designated router or backup designated router communication, : 6. When it comes to EIGRP, it's FF02, : A, because A represents a 10 in hexadecimal. So to recap all of these addresses, because they are pretty important, and these are the ones that you're going to be seeing in the real world, here's what we're going to say about this. The 2000s, when you see something like this, like 2600, 2700, if it starts with a 2, there's a good chance you're talking about a global unicast address, and this is how devices uniquely identify each other on the world IPv6 network. When we look at FC00, this is the standard now moving forward, as opposed to the deprecated FEC0, even though this is still being used. These are the private local addresses. This is like the private address space in IPv4. Still, these are almost never used. There's going to be a very specific use case for them. And as we've already seen, my VMware Workstation Player installation uses FEC0 for the local DNS requests. FE80 is the link local request, and this is how a lot of addresses come to life, and a lot of IPv6 networks perform their discovery and solicitations once they have a link local address. Then lastly, FF0 whatever is going to be the multicast addressing schemes. So that's been understanding the different types and classes of IPv6 addresses. This is how they're going to be allocated. Now, when we're moving forward through the rest of these nuggets, we're actually going to talk about how these are used and designed in enterprise environments. I hope this has been informative for you, and I'd like to thank you for viewing.